down if needed. Otherwise, we can start. Are you ready?
Yes, sir.
Start.
Yes.
Uh, Today we will talk about an aspect of statistical analysis which is considered a bit advanced. The theory for it is taught. Hello? The theory for non-parametric regression is taught only at the postgraduate level. So it requires considerable bit of mathematics. But here we will focus more on the application. So we will talk about the theory to the extent that is needed, but we will not go deep into the mathematical results or proofs of anything. We will not go into proofs of anything. So there are several methods of non-parametric regression that are used. But before I go into those methods, let me just try to understand your familiarity level with this. So, have you ever used non-parametric regression techniques in your work? Did anyone do that? Okay. What about regression? Not necessarily non-parametric regression? No? Okay. So, do you have any idea what regression is about? So, there are various kinds of statistical analysis, right? Now, if there are several reasons why for which this tool called regression is used. One of them is to find relationship between two variables, x and y. Okay. Wherever you have paired data on two variables, you know about correlation. There is you can calculate the correlation, but you can express this correlation is also instrumental in establishing a kind of linear relation between two variables, y and x. Okay, so y can be expressed approximately as a linear function of x, and that is what is the simplest form of regression. Now, why is it important? Because on many occasions, you would like to explain one variable in terms of other. Let me give some examples. One of the examples that I was myself involved in many years ago at the Reserve Bank of India. So the problem that was posed to me was predicting the tariff production in the country using the several indicators like whatever had been the tariff production in the previous years, and also certain factors that that may have some influence on it, like the amount of rainfall that has happened till a particular point of time, and several other variables. So, by using this information, you can better predict what an uncertain quantity is going to be. So, the variables that are used for explanation are called explanatory variables, and the one that is being explained, that is called the response variable. There are other names to it. Sometimes this response is called the criteria variable, sometimes the explanatory variables are called regressors or predictors. In machine learning literature, these regressors are called features. So using these explanatory variables or regressors, you try to explain the response variable. So that's the very basic idea. Now, how do you do that? How do you explain? There are various ways of explaining. I mean, you can form a mathematical relationship. I already mentioned one kind of relationship, that is the linear relation. But these are all hypothetical, right? Now, uh, some part of this relation can be derived very nicely mathematically if you are prepared to make some assumptions. For example, if you have an explained variable or response variable y and an explanatory variable x, then let me use a board for a second. Suppose I want to explain y by some function of x. Okay? I'm trying to explain y by some function of x. And y is a random quantity, x is also a random quantity. So this explanation of y will be a good explanation if the gap between what I am trying to explain and the quantity with which I am explaining, if that gap is small, that's a good thing for approximation. So since this is random and that is also random, we cannot say what it will be in a particular case, but on the average we can try to minimize the square of this. But minimizing the square of an uncertain quantity doesn't make sense. So you can minimize the average or expected value of this. What is an expected value? You must know that. You need some background of probability to know it. Yes, so it's the average value according to the probabilistic average of this quantity. As x and y pairs take different values, there is some values are more likely, some values are less likely. So if you consider this square for all sorts of values and take the probabilistic average, you will like this. Now you want to minimize this average squared error. It's called mean squared error. This is minimized over all choices of this function f. I'm trying to find the best function which explains y very well as possible according to this criteria, that this will be minimized. So then, if I choose my f to be like this, that f x is it is called the conditional average, that is, for a given x, what are the possible values of x and what is the probabilistic average of that. Okay? So this is that probabilistic average. It's called the conditional mean, conditional expected value. So this is a theoretical result that can be shown nicely, proved nicely, using probabilistic tools.
There is an if the value of x is equals to the value of the right side of the x. Or different.
See, x is a random quantity.
So no, that's x not after that x.
Yeah.
So y by x equals to x.
Yeah, y given x equal to x. Yeah.
says that x is smaller x is equals to the fx of the value of the
This smaller x. Yeah. So if I put a real number here, I will put the same number on the
yes,
other
that's
side.
right.
So this is actually definition of a function. So it has to hold for all x. So maybe I can type. So that sounds somewhat mathematical, but essentially what it means is that the function that works best for approximation is this function. How is this function defined? For a particular value of x, consider all possible values of y and consider the probabilistically weighted average value. This actually goes very close to your intuition. You can see that. Uh, so let me erase all that and just say that this is the kind of thing I'm looking for. When my son was 2 years old, he his height was 3 feet, and somebody told me at that time that this means his mature height would be about 6 feet. He is just short of 6 feet now. Uh, so how does someone make such predictions? The fact is that there are, people have different heights at different ages. So if you consider, let's forget about racial variation. So let's say we are talking about one particular uh, race, okay, one particular anthropology race. So then age versus height or stature, this is they call it. Stature is height. That if you plot for a particular individual, it eventually reaches a mature height. But if you are collecting data, this is not really how people come to conclusions about it. In order to get this plot, suppose I wanted to do this plot for my son, then I would have had to wait for maybe 20 plus years to get this plot, right? Because then I have to observe the height at a very young age, then at successive points of time, in order to be able to get one such graph. This is done, but if you want to find out the large scale behavior of this kind of plot, then you have to do very long experiments. So that is very costly. So people do cross-sectional studies when they do not really wait for that many years, but rather take measurements of height or stature of people of different age groups. Okay? So then what happens is that for maybe 7-year-olds you have a bunch of data, for 8-year-olds you have a bunch of data. So this way you will have many such points which will give you some idea about how the whole thing progresses. Actually, what I showed is actually it is more dispersed than what I showed. Now, suppose I ask you, what is the, suppose I say that I want to approximate the height, which I call y, by the age. So I want to have a formula. some function f of x. So that if you give me the height, if you give me the age, I should be able to tell you the height. That will not be accurate for any particular individual, but on the average it should be fine. If I want to do that, let's see how will you proceed if I didn't discuss any of these things. Suppose pretend that this is not there. I'm just asking you that you have data, x and y, paired data. My question is, what is the average height of people who are aged, let's say 12 years? I'm talking about males, let us say, not females, so that kind of heterogeneity is not there. So stature of males at some age, let me say this is, suppose this is 12 years, and you have access to the entire data, what will be your average, what will be your answer? And of course, I can repeat this question for every age. So that means for every x, I'm trying to get some fx. So that the plot of fx versus x looks somewhat similar to this, and the error that we make is as little as possible. So, how will you answer this question? You have access to all this data.
Average line to be made. We have to average line to be made between y and x as per the x and y.
Average straight line?
It is a
We have to find the correlation between age and year, non-linear by means of non-linear regression.
Okay, let me change the question a little bit. Okay. Typically, in anthropometric studies, people are not really measured for their height at any given point of time. I have actually participated in one such study. Not really participated. There was a study at ISI on adolescents and young adults, both male and female, from some South Calcutta schools and colleges. And I was involved in the analysis of the data. The protocol for that study was that if students from schools or colleges were enrolled for this study, their parents were asked for consent, and if the parents gave consent, then some body measurements were taken, professional. Now, this was done. People took great care to make sure that every student is measured, the height and other dimensions are measured on or around the time of their birthdays. If possible, on the birthday, if not possible, maybe plus or minus 1 day. Why is that? Because then you will be able to collate data. So you'll have observations on the height of many 7-year-olds, many 8-year-olds, many 9-year-olds. So the plot will not really look like this. Plot will look like something like this. So for age 12, you will have a bunch of data. So all these data points are for age 12. Then again there will be a set of data points for age 13 and nothing in between. Alright? So this is the kind of data that emerged from that study. Suppose this had been the kind of data, and I ask you, give me a number which best approximates the age of a 12-year-old.
Mean value.
Huh?
Mean value on that.
Mean value of 12-year-olds, right? That is exactly what this is. Put x equal to 12, that means you are controlling the age at 12. And considering all y's, so some of these y's will be heights of very short people, some of these will be heights of very tall 12-year-olds. Most of the heights most of the measured heights will be around the middle, around the most likely value. right? So in the data, which values will have more occurrence? Very short people will not be very many. Tall people will also be, extra tall people will be rare. But people of average heights for that age will dominate that data. So when you take the simple average, by sheer majority of the likely values, what you will get is a probabilistically weighted average. So that is the empirical counterpart of what is coming out of the mathematics. What is claimed to be the best predictor, the empirical counterpart, the sample counterpart of that is the age-specific average height. And as you have seen, that it comes out in the discussion as a very intuitive solution to the problem. And that intuitive solution happens to be mathematically the most optimal solution according to the minimum mean squared error criteria. So that is this additional expected value, additional average value, occupies a very central space in the theory of regression. In fact, it occupies such a central space that it itself is called the regression of y on x. This is called the regression of y on x. But from the theory, it is actually not the most general description of regression of y on x. It is specific to some idea of optimality, like we want to minimize the squared, average squared approximation error. So if that criterion is used, then the optimal solution is this. But this criterion itself is very commonly used, very popular criterion, and because of that, the solution to the most popular criterion is referred to as the regression of y on x. It's like, the Xerox is a very popular kind of copying machine, so people call it Xerox machine. It's like that. And this is called the regression of y on x in a specific sense, but popularly it is used in a very general way. Now, once you know that this is the regression of y on x, there are several questions that come up. Now, I was able to give a nice answer to this because the data was of this type, that for many 12-year-olds we had the height data, so we can say what is the average height or a typical height. If I want to approximate y by some function of x, it will be the age-specific mean. Okay. But suppose, so I can do that for age 12 and age 30. What do we do for age 12.5? Maybe you can say that you will do some kind of interpolation. That can be done, but so if I do that, then it will look something like this. So there will be a mean of 12-year-olds, there will be mean of 13-year-olds. So we'll connect them, and by connecting several such things, you will get a graph like that. Correct? Now, how good this estimated chart will be depends on how much data you have, right? And if you have a large scale study, which is rare, then for certain ages you have more information and in between you have less information. And so it is that area where you have lack of information that you will try to make use of some interpolation. Okay. Now we statisticians spend a lot of time on this approximation, whether you can marginally improve it. Maybe if you are looking for a cut and dry solution, very quick solution, this is good enough. But there can be multiple ways of doing it. There are alternative ways of coming up with an answer, and all these answers will not be equally good. Some answers will be better than others. Let us see in what sense. Okay. First, this idea will work only when you have a controlled experiment. That is, you go and visit students on their birthdays and measure their heights. Not all regression problems are not so controllable. Sometimes you have observational data. Y and X are given to you without your having any hand in designing the values of X. So if that is the case, then for 12-year-olds, you may not have too many observations. And if you do not have many cases to average over, the estimate will not be good. Right? So what will happen in that case? So then the plot will look something like this. That suppose you have X values scattered all over the place. Like I had drawn previously. Like this. So then, at this height, you may have only one data point. And sorry, at this age. Maybe here you have two. So this way, so you connect them, these two. And then, at every single age, you may have just one or two or at most three data points. And because of the variability of the individuals for whom you have taken these measurements, these things may look very haphazard. Very haphazard. Because each of these averages are averages over just one or two cases. And as you know, in your physics experiment, if you do an averaging, your number becomes less erratic, isn't it? Measurements, single measurements are more erratic than averages. So this averages, then because of relatively less averaging, that you get this fluctuating behavior. The earlier plot was such that at every integer age we had a bunch of data, in between nothing. So because of the wealth of data at the integer ages, such fluctuations were not there. But generally for various data sets, you see this kind of fluctuation. So what to do in that case? What kind of method can we use which will work not just for the earlier example, but for examples like this also? Any suggestion? Well, see, it's not a question of using one summary against the other, but the point is, how do you make best use of the neighboring data? See, when you do averaging at this age, you may have just one or two data points. But only, if you just consider the neighbors, here, it's not just one or two, it's more. So if you can somehow borrow information from the neighboring X values, then you will have a larger sample size. So that idea is something that we want to make use of. Okay? Because more data gives me more smoothing, more averaging, less fluctuations. That's a good thing. But if I do that, I think that is one way of looking at it. Now, you can say that you will fit a straight line with this. People do that also. Okay. The problem with fitting a straight line here is that human height doesn't really grow linearly with age. As you see, if that had been the case, then people would go taller and taller and taller and not stop. I had stopped growing from age 20 or so, so that I had not gained any fat. I don't know whether anybody else has any other experience, but yeah, that's how nature of things are. So straight line will not work. Well, when something fails, we come up with a little variation, parabola, maybe quadratic. So if you use a quadratic, it will be a parabola, it will look like this. That may be resonant. Okay. But soon you will see the limitation of this kind of approximation. The moment you see more general types of variation. Okay. So suppose your data had looked like this. I'm not talking about stature anymore. I'm talking about dependence of y with x. So that can be of any nature. So let's say I have something like this. If this is the kind of pattern, you can see that it's possible to fit a function like this. So we can fit a function like this, but it's not a parabola. It's not a straight line, it's not a parabola, it's not cubic. But somehow by looking at the plot, this looks right. At least reasonable. More reasonable than straight line, more reasonable than a parabola. Right? So, what description should we use for a card like that?
Is it basically a sine curve?
Well, sine curve also has its limitations.
Yes.
Okay, every specified function has its limitation. So how do we make it more flexible? See, now we are actually trying to specify this function. We are trying to build a model for this function. The straight line model, which is called linear regression. So that there, the model is that the expected value of y given x equal to x is a plus b times x. So this is the assumed model. So you assume this functional form of fx. And then from the data you estimate a and b. So yeah.
For this we can use the logistic regression model, polynomial regression model for two best fit.
No, we cannot do that because for binomial regression model, this y has to be binary.
So no polynomial regression model.
Well, polynomial we can use. Polynomial definitely we can use. So what you are saying is that instead of using this restrictive structure, make it more general. Now, how much more general? Okay. So polynomial is one answer. The problem with polynomial regression is that if you want to fit a single polynomial to a fluctuating data set like this, then you will need a very high order polynomial. And the problem of fitting a high order polynomial is that it is susceptible to poor estimation wherever you have shortage of data. Okay. So your data may be very dense in some place and not so dense in other places. would be like this, that here you have less data, here you have more, and again you have less data in some places. So wherever you have less data, you know less. Your knowledge is limited. Okay? But your polynomial regression will not spare that. It will treat every observation, every axis equally, and then try to fit something that goes very near to everything. But that means it is susceptible to errors. Okay? So it is here that non-parametric regression becomes a useful alternative. So what is non-parametric regression? We will not use a specified functional form. This is parametric regression. That is, you presume that fx is of this form, but leave one or two parameters unspecified, estimate them from data. That is parametric regression. But here, what the approach that we are going to take is that we will not presume any particular parametric form, but rather try to rely. That doesn't mean that we don't assume anything. We assume that the function that we are trying to estimate is somewhat smooth, and we'll try to exploit the continuity to come up with some estimate. Okay? So I think I'll stop writing on the board now and give you the slides. This I thought I would spend some time on this because you said that you didn't hear about non-parametric regression before. So this introduction is inside. Now let's see, there should be a break, and what should be the time of that break? 11 or at what time? 11, right? Okay. Do you have any question on the part that we have discussed so far? Okay. Now, so, who is the ops? Can you read it? I suppose it's okay. Okay. So I was talking about that fx function. So that is that conditional mean. That is conditional average, let's say. But another way of writing that is that the actual value of y is that quantity, some function fx. That fx is what is called mu x. So actual y is that mu x plus some deviation, and that deviation is random. That is the model assumption. So the key thing is that we are not assuming yi is equal to a plus b xi plus error. We are not doing that. If we had made that assumption, then this would have been parametric regression. Okay? So we are leaving the functional form of mu or f unspecified. Okay? Now, how do we estimate mu? This is the first technique, kernel regression or kernel smoothing. Estimate mu without assuming model. We will talk about several solutions to this problem. The first solution that we talk about is this kernel regression or smoothing. And we'll also talk about a variation of that called key nearest neighbor smoothing. Then we'll talk about local polynomial regression or lowest regression. You may have heard these terms. You said that you didn't use non-parametric regression, but these buzzwords fly. So you may have come across these words here and there, or you may come across those later. So today, at the end of this class, you should be able to say something about this. You have some knowledge about it. Then there's blind regression. and integration tree, and then banking and urban forest. I do not think I will have time for anything else, but this, we may not even have time for this. Let's see. So here is the first thing, kernel integration. First thing. What is the strategy here? Look carefully. This is actually a weighted average of the values. What I am trying to do is to estimate the function f that I have written on the board, and it is, I am using the notation mu for the same thing here. I had come prepared with the slides, I forgot what notation I used in the slides, so I wrote fx. Otherwise, I would have written mu x there on the board. Okay? So it is that function that I am trying to estimate. The model, the estimate is nothing but an average, a weighted average of the yi values in the data. The data is of the type xi, yi equal to 1 to n. That is the form of the data. And then I have a weighted average. So what we call this, let's say I call this k in wi. So this is summation wi yi divided by summation wi. So that's a weighted average. How is the weight defined? That depends on where we are estimating mu. See, this mu is not just a number, it's a function that we are estimating. So for every x, it should happen that way. Now, we define the estimator as a weighted average, but depending on where we are estimating x, the weights change. The yi's are the same for the entire data. But if I am estimating mu x at some x, then according to that, I choose my weights. The weights are large weights if this xi corresponding to this yi is closed weights, and otherwise it is small. So how does that happen? This k is a function that looks like this thing. That k is less for away from 0 and has a larger value, right? Is equal to 0 or close to 0. So that means that when for a chosen point x, I am looking for all the neighbors of x, then the near neighbors will have more, smaller value here. Near neighbors will have smaller value of the argument of k. Therefore, k will be large for the near neighbors and k will be small for the far neighbors. So, the weighted average will give more importance to the near neighbors. So, let's try to map that to the age versus height problem that we are talking about. And let's say we have heights measured not necessarily on birthdays but throughout the age scale. So then, in order to define the age specific mean height, what we'll do is take, let's say I'm doing that for x equal to 12. Then for 12, we'll consider all those xi's and yi's that are there in the data. Some of these data points will be for ages close to 12. So some xi's will be close to 12, some xi's will be equal to 12, some will be close to 12. So those are the ones for which this is either 0 or close to 0. For the other data points, this will be larger. And if k is a function like that which is has a large value at 0 and on both sides of 0 it is range. So then all those far neighbors will have less weight and near neighbors will have more weight. So in that average, which we are computing for age 12, the heights of those subjects will get more weight which are of age 12 or close to 12. So that is how we give differential importance to different parts of the data. For a particular x, we give more importance to near neighbors of that x in the x scale. So those y's are given more weightage. Okay? So this thing is that very intuitive thing, that is weighted average of the data with more weights given to those y's for which x's are close to the point where we factor. So this is what is called Nathan-Watson kernel estimator. It is called kernel regression. It is called kernel smoothing also. So K is a kernel or window function, and this H is the bandwidth. See, I have not talked about H so far. If H is large, that means you have a very relaxed definition of what is a neighbor. If H is small, then you are very choosy. That is, small deviation from X will make it a far neighbor if H is small. And if H is large, then even an xi which is quite some distance away from X, that will become near neighbor. So H is basically the length of the neighborhood. Okay. Neighborhood scale. So it's called the bandwidth parameter, sometimes it's called the window width parameter. And one of the ways that people use this, okay, maybe I'll come to that choice of H later, but I have discussed a lot of things without showing any data analysis. Let's show you some data analytic example, computation of this estimate and how it works. Okay. Any question?
Yes, sir.
Yeah.
So, is there any procedure to select H?
Yeah, I'll come to that. Let's see some instances. I said that if H is large, then something happens. If H is small, something happens. Let's see the demonstration of all of that. Then we'll see how to choose H. Okay? So here I am simulating data from a model. I'll share this code with you so that you can run it on your own later. So I'm fixing a seed so that I can repeat the numbers when I run it again. So what I'm doing is, this is an artboard. I'm generating 500 random numbers from the uniform distribution. So that gives me x. And then this mu is a function which I have defined as sine 6 pi x divided by 6 pi x. Sine x by x kind of function. Okay? And then with that mu, I add some random errors to create my response y. Okay? So I have 500 pairs, x and y pairs. And to see what this is, okay, first let me form a data frame, that is a structure that we'll use here. I'm using, I could have done this simulation without forming this data frame, but I'm trying to get into format which can be replicated for real data analysis. And in real data analysis, this data frame is what you start from. So first let me create that data frame, and then as if I did not know what the sample size, I'm trying to extract the sample size from the data frame. So from line 9 onwards, the code is for data analysis. Till that it was data generation, and I'll pretend that I didn't know how the data was generated. We treat it as the data has come to us. But the advantage is that I actually know where the data came from. So I know if I get a bad estimate of mu, I'll be able to compare it with the truth and say that it's a bad estimate. So that's the idea. So now let's look at the plot. Okay, so here it was showing some immediate variance. So let me use the entire space for the plot. So this is the XY scatter looks. Okay. doesn't look like a straight line pattern, it doesn't look like a parabolic pattern. It is actually sin x over x kind of function, but the scatter doesn't look like even that because of the noise, because of the added noise. Okay. So what is the function, the true function? It is this one. Okay. So this true function, this is the last time I'm using, well, I'll use it for comparison later on, but this is not part of the data analysis. Okay. You can ignore this black curve because it comes from the data synthesis part. Okay. Typically for data analytic problem, no one will tell you what the true regression function is. Okay. You will just have this y versus x data. Now let us see whether we can do a reasonable job of kernel regression. Okay. So for that, we will use this function called k-smooth, and it's a very simple thing. If you type help k-smooth, so this is the function. So the help of that shows how it is, what is the usage and all that. And sorry, this is not true. So you can see that it comes from so-called stats package of R, which is the default thing. You don't even have to install it separately. So if you have R installed in your computer, then stats is automatically installed. And part of that is this case mode. So this function is very easily accessible. It's not very versatile. You see that very easily here. You see the kernel that is allowed here. There are only two choices of the kernel that are allowed here. One is the box kernel. Box kernel is this one. I have shown you several types of kernel function. Box kernel is this rectangular function, the red one. This is called the box kernel or rectangular kernel. And the other ones are triangular and several other names are shown here. Now, going back to this thing, this k-smooth function allows the normal density as the kernel and the box function as the kernel, only two options. So if I use the box function, then this is the kind of so then the kind of smoother that we get from the box kernel is this one. Now tell me, by comparing the estimator with the truth, how good my estimator is. Tell me something qualitatively. Tell me a good thing about this estimator. If you are tempted to tell me the bad thing about this estimator, what is bad about this estimator? You see what the estimator is? It is the one which is fluctuating here and there. The black one is the truth, and this estimator is this. Okay? So what is bad about it? That it is fluctuating a lot. What is good about it? That in spite of the fluctuation, it is generally
maximum data is covered by this curve.
Yeah. So it is not very far from the truth, but it just jumps around. Okay? So something has to be fixed about it, but it's not that bad. Okay. Now I'll use another function to produce the same result, which is a little more versatile. This GPLN function is part of another package. It's called GPLN package. I can find out by typing GPLN here. Yeah, it is part of the GPLN package. So if I use that, then this gives some other choices of the kernel, and it turns out that this uniform kernel is not a very good kernel, that box function, because its neighborhood is very dramatic. When you say that this is my neighborhood, and if you use the box kernel, then everybody who's in the neighborhood is given equal weight. and everybody who's outside the neighborhood is given 0 weight. So neighbor with a slight change in the bandwidth H, or don't have to change the bandwidth. So at X you are computing this with certain neighborhood. Then you want to do it for another X. So with that little shift, some neighbors dramatically lose their importance. And some other neighbors who previously had 0, didn't even count as neighbors, become full-fledged neighbors. So this dramatic change with a little shift causes excessive fluctuations. So that is why the rectangular kernel is not preferred. There are several other options that are there. So here, let's try to replicate this by using this function BPLN. So please notice carefully, when I run this line, only the color of the line will change. That means the new computation will coincide with the old computation. Yeah, I have done that now. So earlier we had this graph of this estimator. We are actually computing the same estimator through another function. But in the next line, I am going to do it by replacing the uniform kernel by the triangular kernel. Okay? So and then the result will be slightly better. Okay? Not a great deal better, but slightly better. It doesn't have that jittery thing. If you shift your X a little bit, it doesn't change drastically. So that problem is not there. But still, there is a problem that it is too much fluctuating, and that can be done, that can be arranged somehow. Just a second. Triangular tablet. Let me first show which is which. The two main function is the black one, and then between the two estimators cannot be distinguished. There is the blue one and the purple one. One is lying over the other. No, sorry. The blue one is the better, the triangular kernel. Then this uniform kernel is the one which is overriding the previous one. So it's not showing anything. Now, what's the effect of this bandwidth? I was saying that using a larger bandwidth H means that your neighborhood is larger, and so you have more smooth. So you're using more data to arrive at your estimate at a single point. So it will be smoother. Okay. That is for larger H. So I'm repeating the previous computation. Bandwidth 0.01 produces this, and if I replace that by bandwidth 0.2, then we get that. So same function, kernel regression computation with a different bandwidth. It produces a dramatically different. So which one is better? Well, situation as the purple one, but we did somewhat off the mark.
But maximum data not forward for 0.2 point.
Yeah. So we are actually in the middle of a trade-off. We have shed some of the fluctuations, and in extent what we got is we got far off from the truth. And this is a typical trade-off in statistical data analysis. This is called trade-off between bias and variance. Variance you can easily identify with fluctuation. So this version with a smaller bandwidth has more variance. Since it has more fluctuation, you can guess that this has more variance. This one has more bias. Bias in what sense? Bias is the error that you commit on the average. You are estimating something, but on the average, your estimator is different from what you are estimating. Okay, so bias is that. I mean, getting off the mark, basically. So this is getting off the mark. Okay, so this one here the bandwidth is too little. Here the bandwidth is too much. So we have two extremes: high variance, high bias. So the question is, can there be anything in the middle which is neither too bad in terms of variance, not too bad in terms of bias? So that is where the question of optimizing the bandwidth comes in. And here, okay, so one more thing that I want to talk here is the true value, true function. So now you can see the same estimator, Nadara Watson estimator with two different bandwidths. The true function is shown there. The true function is the best, of course, but among the two estimators, the one which has more fluctuations is closer to the staying close to the true function, and the one that has less fluctuation is going off, far off from the true function. So that's the trade-off between bias and variance. Now I'll tell you what how we can choose the bandwidth. The idea is that this is a popular way of choosing the bandwidth. So what will you do? You leave out one data point from your entire data set. So when you leave say the IFPS is left out, then the estimator that you get becomes different because your data set is one less than what it was. So I am using the notation mu hat with a minus I to indicate the same estimator computed on the basis of a shorter data set, which is same as the earlier data set, but the IF case is removed. Why do we do that? Because I want to reconstruct or predict the y corresponding to that xi by using the estimator based on everything else, not using that data point itself. So I leave out the IF case, compute mu hat, evaluate mu hat at xi. Xi is the x corresponding to the y that I have left off in computation of that. But after computing mu hat without the if case, I evaluate it at the if and compare that with yi. So in that way I am being very fair that I am not using my data point in constructing the estimator. I am just predicting it independently of that data point and measuring how good that prediction is compared to the observed value. So the difference is the prediction error. So this is the squared prediction error. It's called leave one out cross validation error. Cross validation because we are leaving out one data point and reconstructing the data, predicting the data value and validating, okay, by comparing with the actually observed value. So that's what this difference is. So this cross validations error, if it is squared, it becomes squared error. And this is the cross validation sum of squares with 1 over n, it is the average of squares. Okay? So cross validation average of squares is this one. Now I can have my different values of the bandwidth, but as they say, proof of the pudding is in the eating. If it tastes good, then the recipe is good. So whether you have too much bandwidth, too little bandwidth, what will eventually settle the issue is which choice of H gives you better prediction. And better prediction of a particular y for which that y, that x and y was not used, okay, in constructing the estimate. So by minimizing this, we can get a suitable choice of H, and this is a very popular way of constructing. So let me show you how this is done. So I set a range of H's and then evaluate this criterion over a grid on this range, okay, and then see what happens. And this the criteria is plotted against the different values of H, and the minimum occurs here, okay, so around 0.04. So that is the minimum value of H. This is the value of H for which the cross validation criterion attains its minimum. When I use that value of h, which minimizes the criterion, then this is the plot that we get. So this is a more complete version of the previous thing. So here I am showing earlier choices. I have previously used this choice, which gives a lot of fluctuation. I have previously used this one also, h equal to 0.2. That was the one which was very smooth but off the mark. And then this is the choice that comes from the optimal choice, optimizing the cross validation criteria. And that is what produces something which is very close to the truth. Okay? So it is better than the other things. So let me plot this thing again without those two interfering things. So plot this one and then I go straight into this one. Yeah, now you can see the optimal, the ordinary regression estimator with the optimal choice of h and compare them with the truth. So this is better than the other two options that we have. It's not perfect, but it's better than the other two. And it's producing a reasonable result. Okay. So I think this is a good point to take a break. So let's stop. Questions? Continuing with this slide, so far I have demonstrated this Nadar-Watson parallel estimator. I have demonstrated the selection of the bandwidth through the cross validation, minimization of the cross validation criteria. Now I'll talk about small variation of Nadar-Watson estimate. See here, the bandwidth is chosen once and for all for the entire estimate. And remember, this is a function of estimated thing is a function. We are estimating a function. Okay? So for every x, we have an estimated mu x. For every x, we have an estimated mu x. And for each of these, we have x estimators. We have the same choice of h, the bandwidth. The bandwidth is chosen once and for all for every part of the card. Okay? But your data may not be like that. My simulated data is actually like that. There is no concentration of points on one end or not in the middle or not in the right end. But there can be data sets where there are more concentration of points in some parts of the data and rare in some parts with rare data, then again some parts with crowd of data. Right? So if that happens, then choosing a fixed weight for every location may not be the right thing to do. So what this nearest neighbor, k-nearest neighbor regression does is that the window of fixed width is replaced with a window with variable width, but very in such a way that the number of neighbors is fixed. So for any given x, we choose that window, that length of window, which captures a pre-specified number of neighbors. So that way, in a rare region, automatically your window will be wider. In a region where data points are scarce, the window will automatically be wider. In a crowded region, window will be small. So you will be able to make better use of the available data. So if you do that, then what you get is called. So it's a variation of the parallel regression. It's called k-nearest neighbor regression. And so then, let's see the illustration of that. So this is the library NIT from which the function for k-nearest neighbor regression is taken. This is the function. And the estimator that it produces is shown there. So the latest addition to the graph is this one. Okay, the blue one. This is the blue one, which is that. And then we are producing the same thing through another function. This is to KNN length and this is KNN length. These are two are different functions producing the same thing. That's this one. And the predictions here. Okay. It is shown in red. Okay. So that is the KNN regression. And here also, I have said that for every x you determine how many neighbors there should be, that is a single decision. And then for every x you adjust your neighborhood to include exactly that many neighbors. Now what will that number of neighbors should be? That is the question similar to that is will give you trade-off between bias and variance. The more number of neighbors you allow, you will have more smoothing, more averaging, but you will be allowing distant neighbors, and therefore the averaging will be over irrelevant values of y. Because the further you go from the actual place, then the shape of the regression function changes. So you are taking all of that into your averaging. So that is how the bias comes in. So this is again a question of bias variance trade-off. And the solution that is very popular is the minimization of the cross-validation criteria. So in this case, you do not optimize the cross-validation by choice of bandwidth, but the choice of the number of neighbors. So that selection is made here in this part of the code, and the optimal solution, I think we already have too many cards lying on this. So let's show the optimal. So this is the criterion. So minimum happens when the number of sample size is, or neighbor size is 29 or 28, something like that. And another, so the optimal thing is 29. And the minimized value of the cross-validation criterion is this thing. This, I want to spend a minute on this. So what is this? Remember, the criterion was that you minimize the average of squares. Okay. Now, what is the best case scenario for this? Suppose here, instead of mu hat, you actually had the true function. Then this gap between yi and mu would just be the error. Remember, this is the model. Okay, so if you subtract mu from yi, mu xi from yi, the true mu, yi, then what you get is the error on the right side. So, if your estimator is good, then this will be like average of values of the errors, squared errors. And these errors are assumed to have zero mean. So, the sum of average of squares will give you an estimated variance of the errors. Alright. And if you go to the code, we see initially when I synthesize the data from this part of the code, the first few lines of the code, look at the amount of error that I used. This is 0.2 times a normal, standard normal and variable. That means this error part has mean 0 and variance, standard deviation equal to 0.2. So, average of squares or variance will be about 0.04. Okay, that's the true value of the average square error, mean square error. Now, this is what happens when you use the true function in that criteria. So, when you are doing optimization, you cannot expect to do better than the true function. Okay, so the value that you expect to get is around 0.04, and this is the value that you actually get. So the estimator appears to do even better than the true function, And this is just an illusion. What is happening is that by chance it can be little one way or the other. It says that the estimated is reasonably good after optimization over the bandwidth. It is reasonably. The optimization in this case is over the neighborhood size. How many neighbors to keep in the neighborhood. So the value 29 number of neighbors. That gives you the best situation, and this says that the best situation is not too bad. But this figure 0.09, the 0.039 is little smaller than 0.04. And that is an overly optimistic picture because we know that this error cannot be better than what you get from the true function. Okay, from the true function? Yes. Yes.
The true function is that there is a defined function y equals to mu x plus line number 7. So line number 7.
Okay, yes. I know it's earlier.
The true function is defined in this equation.
Yeah, this mu, this true function, line 6 defines the true function.
Okay.
And in the criterion, if I put the true function, then I should, algebraically, I should get the error. Y minus mu should give me the error. So, average of squared errors is approximately the expected squared value. And that we know theoretically should be 0.2 square, 0.04.
Sir, it is approximate. It is the assumption value 0.2. 0.2.
Yeah, so I'm using that for synthesizing the data, so I know that that's the true standard deviation of data. So that was the point, that the bandwidth selection seems to be reasonable. So we are at this stage now. Minimized CP is this. And with that minimized value of, minimizing the optimum value of the neighborhood size, if I repeat this bit, then this is what we get. So k is the number of neighbors we are keeping every time when we choose a neighborhood. For any x, we choose the neighborhood to average over. And the size of the neighborhood is chosen by optimizing that cross-validation criteria. And with that optimal choice of the neighborhood, this is the kind of estimate that we get. That is the non-smooth curve here. The smooth function is the true function. It is the black one. And the red one is the estimate. Again, not too bad. Any question on this? So I will now switch to another method. K nearest neighbor was just a variation of kernel regression. And now I am going to switch to another method, that is the lowest regression. Oh, one more thing that I forgot to say here is that so far I have talked about only single explanatory variables, and I will stick to single explanatory variable. The only thing that I would like to mention is that if you have multiple variables, we are talking in the backside. If you have multiple x variables, then instead of this x mod x minus x xi, you could have a distance between the central value where you are estimating and the different xi that you have. So this will be scalar measure obtained from the vector x and xi. And this is the standard way of doing it for non-parametric regression. But it is also known that this k nearest neighbor or the kernel smoother behaves poorly near the boundaries. So this is a known weakness of all the non-parametric estimators. The point is that near the boundary, you are estimating it somewhere at this point. On the left side, you have a lot of neighbors. On the right side, you have more neighbors. So necessarily, it's going to be poorer than the case where you have more wealth of data. That's the point. Now, this is another class of non-parametric regression, another philosophy. So So it starts from the idea of kernel regression itself. Kernel regression is a weighted mean, but that can be seen, that can be described as an optimizer. Okay? If you minimize this criteria, then the minimizing thing, I mean, suppose you want to find the value of n which minimizes this whole thing. So what constant put here will produce the minimum weighted sum of squared values of yi. I mean, not really squared values of yi, but the squared values of prediction error of the yi. Okay? The weighted sum of prediction errors of yi. And that, if you want to give more weight to the points around x, then the best n which produces this minimum means the kernel regression. Another Watson kernel estimation. It can be shown. Now, the whole purpose of writing it this way is to see this whole thing as, I mean, whatever we have done so far, as the solution to the search problem. The search problem is for the best regression function. Okay? Now that search, according to this criteria, is restricted to selecting an n, a single number for a given x. If that means you are trying to find the best constant that fits the y values around the x. That's the way this problem has been formulated. But suppose instead of trying to find the best constant, you are trying to find the best straight line. Then it will look like this. Okay? What is the best straight line? For which, that means you have to choose the slope and the intercept part, the parameters. So what selection of the slope and intercept parameters is going to give you a straight line which is best for that location. The solution to that is called locally weighted scattered smoother or LOS. If you look at the implementation of this, it will not look like a straight line. It's actually a small straight line at every location. And the moment you shift your location, the straight line changes. So you see a smooth curve, but locally it is a straight line that is needed. And that idea can be further extended that instead of picking a local line, we can pick a local quadratic or a local cubic or a local polynomial. Okay? So this is called locally estimated scatter plot. That sounds similar, but it's spelled differently. LOESS, LOESS. And the most popular choice for LOESS polynomial is a cubic polynomial, and there is this k weighting function or kernel function. This weight function, the popular choice for, in this context, the most popular choice is the tricubic weight function. And there are some theoretical reasons for that choice also. And once that is done, there is still the selection of age that is there. It is not really age, but some other scaling parameter that is age, which is somewhat equivalent to choosing age. Now this alpha is actually the parameter that is optimized over, the parameter that controls the extent of smoothing is the sample fraction of sample size included into it. So far we have seen selection of bandwidth for kernel regression, selection of fixed neighborhood size for kernel for k nearest neighbor regression, and now selection of a fixed fraction of the sample size for LOESS. So these are all equivalent characterizations, but the philosophy is slightly different. Like for k nearest neighbor, the philosophy was to find a certain number of neighbors. Okay, that number will be the same everywhere. And here it is the fraction of the total number of cases. So that is what is optimized. And then for every given alpha there is a choice of age, so we've chosen accordingly separately for every year. And then there is the next, of course, extension to multiple dimension will be similar, but let's see the demonstration of this lowest smoother. First, for some choices of the smoothing parameter, and then for optimized choice of the smoothing parameter. Yeah, so this is local linear. It's actually not local linear, it is local polynomial regression. Particularly in LOESS, it is not the linear one that is used mostly. Okay. So the function that is used is lowest. I leave this code with you so you can explore and find out which package it belongs to. Once you plot it, what is currently being shown is the K and everything. And this on top of that, just now what I have plotted, this is for in blue color. That is the lowest regression shown here for I think the choice of alpha I did not specify anything. Choice of the parameter, smoothing parameter, I did not specify anything. The default choice has been used. So you should not depend on the default choice. I'll now select alpha. This is for the span parameter. By searching over the range of values and then minimizing the CV criteria. This will take a little while. So it's computationally much more intensive than the previous two methods. Among the last two that we have considered, the K nearest neighbor regression is the fastest because it uses the rectangular model. So the computation is the algorithmic simplification that happens when that model is used, and KNN makes use of that. So it's a very fast thing. You get the output in a flash. This is much slower because you are estimating more parameters for every x. So naturally, there is more task, more computation involved. Anyway, now we are done with that optimization and see that among the set of values that we have tried, alpha equal to 0.2 is the best. And once we choose that, the minimized value of the cross validation of squares is again very similar to the one that we found before, 0.0, around 0.04. So which is the best that you can expect because the error variance itself is 0.04. You cannot get better than that. So with that, let us see the kind of smoothing that we get. So these are the two things, the true function and the lowest smoother or lowest regression with optimized smoothing parameter, optimized value of the span parameter. Okay, so this is the lowest technique, local polynomial technique. Now we'll move over to another method. Now, one point I want to make here is that I am demonstrating everything with respect to a single variable. Two variables may be handled, how that may be handled, I have indicated that instead of x minus x mod, we will use some distance between, maybe the Euclidean distance between the x vector and xi vector. But as you increase the number of x variables, the number of predictors or expected variables, it becomes harder and harder, and the performance becomes poorer and poorer. Non-parametric regression is not for the poor. I mean, not for the poor in terms of data. You must have wealth in terms of data to be able to do non-parametric regression. And the data requirement becomes much steeper when you have higher dimensions of your x variable. Okay? So that's also called the loss of dimensionality. That if the dimension of the data grows, your requirement for the sample size becomes exceedingly high. So that is why non-parametric regression of this kind, smoothing kind of thing, is not even tried when you have very large dimensionality of data. The next technique, splines. Okay. So splines belong to a class of regressors which are called basis function regressors. But we'll talk about the spline itself. So, what is a spline? Spline is a combination of several polynomials or other basis functions. Now, in a linear, multiple linear regression, what people do is on one side you have y, and on the other side you have a linear combination of several x's.
Excuse me, ma'am.
Now, instead of having
Excuse me, ma'am.
linear combination of several x's, you can have a single x and higher degrees of it. Okay, so polynomial regression. We are talking about polynomial regression. So suppose I have a single variable, but instead of just a single polynomial, I want to have several things. Say I want to have one polynomial for one part, another polynomial for another part, another polynomial for another part. Then that will give me much more flexibility of the shape and size that we can get by combining these local polynomials. Okay? It could be one sine function here, another sine function here, another sine function here, like that. So these are called basis functions. That is, several functions of x which together are mixed to produce a very versatile class of functions. Because of this versatility, you can use it for non-parametric regression. In fact, the word non-parametric regression is a misnomer. Essentially, you reduce it down to some kind of parameters that you want to optimize. Like in local polynomial regression, what you do? You estimate A and B locally many times over. So here also, instead of using set functions, you use a set of basis functions, and the coefficients of those basis functions are what is optimized. So typically, what people use is low degree polynomials. So you split up the entire range of x variables into several chunks. In each part, you fit a polynomial. That's it. It's not that, earlier we are fitting a straight line or quadratic or cubic at every point and shifting it continuously. So with every shift, your cubic changes, polynomial changes. This is not like that. You have fixed ranges. One polynomial given here over a specified interval, and again another, and these different intervals or these different little polynomials are tied up at the boundaries. These boundaries are called the knot points. Knot. Okay. So at the knot points, you connect them and you impose some continuity restriction because you want your function to be continuous. So that's how it is done. Low degree polynomials joined at interval boundaries called knots. And you require continuity of not just the function but of the lower order derivative. For example, if you are using linear splines, then it will be one line here, another line there, another line there, all connected, no jump, but connected. If you are using quadratics, then one quadratic here, another quadratic here. There will be not only continuity, but the continuity of the derivative also. So that the tangent here will coincide with the tangent here. And what happens if the tangents match? There will be no kink. Okay, so there will be more slope. Not just continuity, but there will be continuity of derivative also. If you use fourth order, or rather cubic splines, then we will match not just the value of the function, not just the first derivative, but also the second derivative. So there will be continuity of the function, continuity of the first derivative, continuity of the second, continuity of the second derivative. That is for cubics. Fourth order polynomial, we will require continuity up to the third derivative. So this way, all lower order derivatives you will require continuity, so the function is very useful. So what happens when you do that is that the number of pre-parameters, because of all these constraints, derivatives, match and all that, the number of parameters is actually the number of knots plus the degree of the polynomial. Yeah, and you can optimize over the locations of the knots also, but today I will not talk about that. If the knots are fixed, then this whole thing is amounts to fitting linear regression, where the basis functions come in as regressors. So the technique is very simple. When you actually see the implementation, you will see that the function used for linear regression is used for implementing this. So let's see then an example of that computation. So this is a single spline, that is the entire range of x is used, and there is no not part. The whole thing, single iteration is used. So then this is what you get with this cubic spline. So same data, you are fitting a cubic polynomial. So this is, it's not going to be very good. But then if you use a spline with 7 degrees of freedom, then you see it is this function ln, R function ln is for linear regression. That is used here. And so the spline is fitted by using that, and it looks like that. Then 7 degrees of freedom are used. That's not very bad. And another thing that I want to show is that here I have not specified the locations of the knot part. I have specified the degrees of freedom, so that automatically determines that since I am using the cubic spline, then and say 7 degrees of freedom, so then number of knot points there will be 4. Okay, so 4 plus cubic 3, that gives you 7. So since I have specified df equal to 7 degrees of freedom, automatically it means there are 4 knot points. Where will these 4 knot points be placed? Now, a simple data analytic solution is based on this principle that we do not want any segment to be short of data. For every segment, we should have enough data to fit my polynomial or cubic linear region. So we cannot sacrifice any interval. So if you want to do that, then no interval should have less data point than any other interval. So that means we have to use the quantiles of the entire thing so that in each part you have equal number of points. So if you want 4 knot points, then you need 5 segments with equal probability. So 20% of the data on the left side, then again the next 40%, next 20%, 20. So that's how instead of specifying, leaving it as a default choice, I can specify like this, knots. Here in the previous use, see here I didn't specify anything, but in this slide I am using the same function with the additional specification. The knots should be located at these locations. So what this says is that at point 2 probability point, covering 20% of the data from the left, then covering 40% from the left, 60%, 80%, and then 100%. So these 5 segments are these are the 5 segments. So that automatically determines where the knot points will be. The knot points will be at point 2 quantile, point 4 quantile, point 6 quantile, and point 8 quantile. So if I do that, then I get exactly the same feed. If you notice very carefully, now I am going to override with black color and it will look the same. So it seems only the color of the plot change. That means whatever was computed by default is reproduced by my explicit choice. So the default was this choice. Okay. So I'm telling you now that if you specify the not parts, then the default option that the program will use is that depending on how many not parts are there, it will split the entire data into equal number of parts so that you have not that many not parts. And that will produce whatever it can. Now this is different from equi-spaced not parts. You could choose to have equi-spaced not parts. Now, in my data, the range of age values is 0 to 1. If I had chosen 0.2, 0.4, 0.6 and 0.8 to be the locations of the not part on the X scale, then I would have got a different result. Okay. Now, it so happens that I generated my data in such a way that X values are uniformly distributed on the 0 to 1 range. But that is theoretical. In the actual data, 500 data points, we do not have exactly the same number of data points between 0 and 0.2, between 0.2 and 0.4, like that. Because of that, the quantiles will not be at 0.2, 0.4. 0.2 quantile will not be at 0.2. 0.4 quantile will not be at 0.2. To show the difference, I am going to show here what happens if the not points are chosen at 0.2, 0.4, 0.6 and 0.8. And I do that and I get slightly different result. Now this would have been very, very different if my concentration of data had been non-uniform. Then there would be drastic difference between these choices. And the prudent choice will be where there are equal, when you choose the not points as equi-spaced quantiles. So that every segment has equal number of data points to keep the okay, so using that, we want to plot the compare with the true function, and this is how it looks. Okay. Then I picked another version of spline where at the extreme ends, so this is local, these are piecewise polynomials. Now these pieces are at different ranges of x. If I choose to use not a cubic but a straight line on the left segment and a straight line on the right segment, that sometimes makes more sense. Because remember, we have shortage of data at the endpoints. Okay. So near the endpoints, we are not very sure how the behavior should be. To fit a high degree polynomial doesn't make that much sense. So for that reason, it will use what is called natural spline. Natural spline is just an adjective. Basically what it means is that if you are using some cubic in all the segments, keep using that, but at the extreme segments, use straight lines. Okay. So if you do that, then this is what you get. Okay. So the blue one. So you can see that the blue one on the left side, it is continuing on the straight path, and on the right side also it is continuing on the straight path. Okay. So this is the difference between the two. In a particular data set, one will be, natural spline may be worse than the other one. But there is a good justification for using that. In fact, it frees up some parameters which you can use for using more outputs. It's just a philosophy that at the endpoints you would not fit too complex spline, too complex a polynomial. Okay. Now, if you compare the standard errors of fit near the endpoint, you can see that the later one produces slightly more error here. Because here you are constraining it to be a straight line, in this case it turns out. So what I have shown here is the fitted, the error of fit in the last 5 points. Last 5 points means right end. At the right end, natural spline seems to have more error spline, then cubic spline with same degrees of freedom in this case. Okay, now there is another concept. So natural cubic splines I have already explained, so I will go over to the next slide. I don't have much time, so I'll just try to do this. So one thing that we will not be able to cover is dimension. So what is this smoothing spline? Smoothing spline is similar to the splines, but you instead of using fixed length intervals, you choose point between the intervals between observed data points as your intervals. So between every two consecutive data points, you fit a polynomial. Okay. So if you have n data points, you have n minus 1 intervals. Fit a polynomial in every interval. That seems like an overkill, isn't it? Too many intervals. Okay. But what comes to the rescue is the penalty term that is used in the objective function. This is what is minimized. Okay. And how is it minimized? That the first term is innocuous. That you have your observation, you have your fitted model, UX, and you try to minimize the sum square. So this will be smaller if the fit is better. No doubt. But look at the other term. What is it? It says that mu has to be a smooth function. It should not only have a first derivative, it will also have a second derivative. And it should not have a very large second derivative. If the second derivative is very large, what does it mean? First derivative large means high slope. Second derivative large means very steeply convex or steeply concave. Right? Very quick change of slope. So this quick change of things is what makes the function crooked. I mean, putting a penalty on that, I mean, not allowing the function to have large second derivative makes the function smooth. Okay, so this term pulls this fitted function towards as much smoothing, as much fitting as possible. It is favoring fitting. The second term is favoring smoothing. If you fit too much, then you get a overfit, right? But the function will not be very smooth. Right? So that's why this penalty term. And we'll see in a minute the implementation of this. So this interpretation is given there. The first term is a penalty for misfit, the second one is for roughness, that is opposite of smoothness. And the best function comes out to be, this is a theoretical result, that if you minimize this, then the best function among the class of all continuous functions is a cubic spline. Cubic spline with knot points at every data point. Okay? And that is called the smoothing spline. In spite of having so many segments, it is not very tough. And we'll see the proof of that. But how much tough and how much smooth, that is controlled by this parameter lambda. So again, that can be optimized over, like in the previous method. So let's see very quickly an implementation of that, and then we'll stop. So this is the smooth spline implementation, and on the previous things, if I plot the smoothing spline, then this purple one is what you get from the smoothing spline. So it's quite respectable, you can see, compared to the other things. This is producing a reasonable result. And the last thing that I want to show is that this function can be controlled by something called the degrees of freedom, or also by that lambda parameter. So it's not just that these two things will not be directly comparable, because this df equal to 7, if you increase, then it will produce more fluctuations and better closeness to the data. And less degree of freedom means more smooth function. And lambda achieves the same objective differently. So these two values do not correspond. df equal to 7 and lambda equal to 0.001 do not correspond. That's the only reason why these two curves differ. Otherwise, they come from the same kind of fit, So if you are able to correspond these two parameters, then the resulting estimators will be identical. So the point of showing these two is that there are two ways of controlling the smoothness of the fade. One is to the lambda parameter, the other is for the degree of freedom. So that brings me to a close of this class in terms of time. So I will not be able to cover the last item, which was the regression trees and random forest. But that's okay. Too much of anything is not too good. Okay. So what are your questions?
Sir, can you show the random forest graph?
Random forest.
Yes, sir.
Okay. So I am not going to the theory. I'll just show you how it would have looked. So the tree, the first part is showing the tree model, but let's go. This is how a typical tree fit will look. Piecewise constant. Okay. And then the random forest fit will look like. See, that is computed by resampling from the data and generating many such trees and averaging over them. So that is so what's going to show is not really random forest, it's called band trees. That's a state, something in between trees and random forest. So the averaged trees that will produce, this is another way of generating the same tree. So this is a single tree, and then through that tagging and eventually so this is the average of that tree. So this is what you get here. Now I will not be able to show random forest for this data set because for random forest you need more variables. Here I have a single variable, so it cannot be. See, this is kind of randomized selections of subsets of data and repeating the same estimator, averaging over those. So this average over tree is producing this. Okay. But random forest does another kind of averaging. That averaging is over random selection across variables. Here I have only one variable to choose from, so I can't demonstrate that. But I had some other thing with many variables that is there in the code and also in the description. So we will be able to see that. I will leave the code here, so we will be able to run it slowly at your leisure, and we will be able to see that.
Thank you, sir. So what dataset is using for this?
What
Dataset
is-
name?
Here I have used a simulated data set. I have shown you my hands. Everything was, see, at the beginning I had synthesized this data set. This is simulated data set. Because I wanted the truth to be known. I was comparing everything to the true function of the x. Okay? And for the random forest illustration, there is a housing, Boston housing data set that is used. This one. Okay. So you can go over the steps and see how it's done. Yeah.
If there are big data, then the degree
If
of,
there
if there is a big data,
are,
then the degree of freedom will be high.
yeah, so big data, in this example, probably what you mean is that you have a single y and single x, but the sample size is very large.
Yes, sample size is large.
Yeah.
So that time should be approximate by cubic span, that means in the segmented form, or how to minimize the degree of freedom, because otherwise the function is not smoother.
No, it's not, the degree of freedom is not the right thing to minimize. See, if you are richer, then you spend more. If you have more data, then you use more complex function. It's just like that. So how do you decide how rich you are? Okay, you call somebody to assess your wealth. So here that is assessed by this CV here, cross validation criteria. Okay, so for a given data set, you can achieve a compromise between this bias and variance by optimizing over whatever smoothing parameter you have. For kernel regression, it would be the bandwidth. For k-nearest neighbor, it will be the number of neighbors. For smoothing spline, it will be the alpha parameter. So these are all smoothing parameters for different things. Sorry, not smoothing spline. It's for local polynomial, it is the alpha parameter, lowest. For smoothing spline, it will be the number of mods. converted into degrees of freedom. So you can optimize over this smoothing parameter and make a judicious selection for your data set. And you will find that for a data set, suppose you have obtained some optimum choice. If you take a subset of that data, randomized subset, I mean maybe half the size or 1/4 the size, then your optimum selection of your smoothing parameter will change. Because for the smaller data set, if you are poorer, you spend less. Right? That's the way.
Any other question? Any other queries? Anyone have any queries? Sir, I have one silly question, silly query. What should be the optimum key in the K neighbor? Optimum key means what?
Oh yeah, I talked about that. This is chosen. See, there are two ways of answering this question. One is theoretical. The theoretical answer comes from theoretical analysis of the rate of convergence of the bias and variance, and then there is a theoretical answer to that, which tells you at what rate it should go. It should converge fastest. But that has no practical value. When it comes to actual data analysis, the solution that people uses is this minimization of the cross-validation criteria. Now, it's the most popular criteria. What I have talked about today is leave one out cross-validation, but there can be random partitions of the data split into a training set and a test set, and then doing that multiple times and averaged over. So that can give you a more robust criterion for selection. But this is a very basic version of that, where the test set is of size 1 and the training set is of size n minus 1. So that is repeated and minimized.
Thank you, sir. Once again, I want to thank Professor Devashish Sengupta sir. Sir, it's a wonderful session that you have enlightened us, and I think we know the basic, and we just captured the basic understanding of this non-parametric kernel regression. So I think anyone having any questions, you can ask. Sir is here.